We're really happy you're here, and we're happy to have Dr. Ron Polidan with us. You'll hear a little bit more about him in a moment, but first I just wanted to introduce myself and tell you about our program and our partnership with the library. So my name is Heather Ingram, and I'm the program manager for the Osher Lifelong Learning Institute here in Bend. And we cover Central Oregon. It's a program for adults we say 50 or better who want to learn for fun. And we have non-credit classes and study and discussion groups all year round. We have a few different venues. We're really happy to be here at the library and be doing these first Friday talks. We have 2 more planned for sure in May and June. And Liz and I will coordinate about whether those continue July and August, but May and June for sure, we will be back. And actually our May speaker, where's Ben? Saw him in the back. Ben, there he is. So Ben right here, he will be speaking in May about the Florida Everglades. So that'll be exciting. And then in June, I believe it'll be an architecture talk or art history. We're still working out the details on those. So we are a lifelong learning program, and we're happy to partner with the Deschutes Public Library. They're providing the venue. We're bringing you the speakers. If you want to know more about our program, we have our separate sign-in sheet in the back. I won't pass it around. But it's in the back, and then we have some brochures with information. And several of our members, if you'll just raise your hand if you're a member of OLLI, several of our members are here today and online as well. So welcome to all of you. And at this time, I'm going to have Russ Hopper, who's one of our members here in Central Oregon, introduce Ron Polidan, who will be giving our talk today. So
should I stand there?
Yeah, I think so. Or, just walk up.
In here somewhere.
Yes. Yep.
Good morning. I've been a member of OLLI since 2008 and have been president, been on the governing council, and been on programs. So as you might guess, I like it. And I imagine many of you would too if you joined. So let me introduce Ron. He's an astrophysicist / space technologist who retired and moved to Oregon in 2016 and lives in Terrebonne. That didn't work out real well for Ron. So he unretired in 2020 and is currently employed by Lunar Resources, Inc., a space industrialization company based in Houston, Texas, as the director of programs. He has over 45 years of space mission experience, working almost equally amounts of time in academia, government, and industry. His previous 2 employers were NASA Goddard Space Flight Center from 1989 to 2004 and Northrop Grumman Aerospace Systems 2004 to 2016. At Goddard Space Flight Center, he served in a variety of roles, beginning as NASA's project scientist for operations for the Hubble Space Telescope. And prior to its launch in 1990, up to the first Hubble servicing mission, and ending as the center's chief technologist, overseeing all technology development in the NASA Center. At the Northrop Grumman, he worked in civil science sector in a variety of roles, manager, director, and chief architect, overseeing the development of new science missions and related technology. Sounds like he's well qualified for our speech. Ron?
Good morning, everybody. Today, I would like to talk about the first results from the James Webb Space Telescope. My plan for today is to give you a brief introduction. And part of this is to help you understand the data that I'm going to be presenting. I'll give you a little bit of history because I think the history is a bit important. And then also to provide some technical context. And the goal of technical context is not only to let you understand the data a little bit better, but also the data from James Webb is coming out weekly. And so there's all kinds of new things showing up. And some of the context I'm going to give you is intended to let you understand these new observations that will come out a little bit better. So you can impress your friends and stuff by giving them insight into what the data is. And then I'm going to get into the science results. Now, there are new science results coming out every few days from Webb. So if you wanted me to talk about the scope of things that they have observed, it would take me a couple weeks. Since no one wants to sit here that long, what I've done is pick a couple of highlights, primarily to show you the scope of things that Webb would likely see over the next year or two. And this is less than a year old. It launched on Christmas Day in 21. And the science data is still being refined and coming out. But almost all the results that I want to talk about today are preliminary, and I'll get into that. The one thing that I want to stress is that there is a website, and it's here at the bottom. It's a really great website. They post images. You can download images, so anything from extremely high resolution to thumbnails. And they provide actually some very good discussion of what you're looking at. So this is a much better website than has been done in the past. So I strongly encourage that you look at it. So to get started, why do we build big telescopes? And there are two reasons. The bigger the telescope, the greater the sensitivity, and the higher the resolution. And resolution is set by the aperture of the telescope or the lens, not the number of pixels. So the bigger the telescope, the more you're going to see, both in terms of you'll just see deeper into the field you're looking at, and you'll get higher resolution. And an example of that is in the lower left. This is the same part of the sky as seen with two different space telescopes. The image on the left is from the Spitzer telescope, an infrared telescope, and this is basically a small galaxy near the Milky Way. And on the right is the same field taking the same waveband, but with James Webb Space Telescope. And you can see the dramatic difference. And so in terms of sensitivity, Webb is roughly 50 times more sensitive than Spitzer. And in terms of resolution, it's about 7 times more resolution. And so you can see why astronomers want big telescopes. The information you would gather from the left image is much less than the information from the right image. The other problem astronomers have is that astronomical objects emit at all wavelengths. And unfortunately, we can't develop a telescope or a sensor that can see everything. So we have to decide how we're going to optimize the telescope. And for an example of that is the pictures in the lower right. This is the Andromeda Galaxy. In the lower left corner of this, you'll see the optical image, which is the one that you see most of the time. And then if you go to the right in the lower panel, you go to higher energy ultraviolet and even higher energy X-rays. You can see the galaxy changes appearance considerably. If you go to the top panel, these are lower frequencies. You go from the infrared to the microwave to the radio. And you can see the galaxy sort of maintains the same appearance, but it does have very different characteristics. And each of these give us unique insight into aspects of the object. So this is one of the reasons why we have many telescopes, because each is optimized for the waveband of interest. So one of the comments that I wanted to make, just as a side, is that rewriting the science books. A lot of the media have made comments about some of this new discoveries that are just not what we had expected Webb to see, as somehow being distressing. It's actually the complete opposite. This is extremely exciting. We go through a lot of effort to build these telescopes, and so we want each telescope to completely rewrite our science books. Why would we spend all this time and effort to build something that's going to tell us something we already know? And so the goal here is to really have every mission, whether it's a planetary mission or an astrophysics mission, is always expected to rewrite the science book. If it doesn't, we fail. For astronomy, this is really a big factor, because understand that everything that you see around you is less than 5% of the universe. 95% of the universe is dark energy and dark matter, and we know nothing about it. So the fact that we, from less than 5% of the information we need, can not correctly predict the distant universe does not come as a surprise to me. I'm surprised we're doing as well as we are. And so the goal here is for Webb and some of these other telescopes to supply that information. And there was a great quote from NASA's John Mather. He's a Nobel laureate, and he's the JWST senior project scientist at a science meeting in December. He's talking about all the unexpected discoveries in the early universe. And he said, there are an awful lot of them. And he's talking about galaxies. Too many, too big, too bright, too hot, too mature, too soon. That is actually extremely exciting in the community, and has already generated a whole bunch of new research studies. It's not distressing. So when someone comments about all these unexpected discoveries, of course, well, why would we build it if we didn't want those? So then the other question I want to get is how do we build them? These are national programs. I mean, Webb took over 20 years to build. So we go about this very carefully. And every 10 years, the National Academy of Sciences works with NASA and the astrophysics community to set science priorities. And they actually set them for both NASA and for NSF. And it basically dictates what they're going to be doing for the next decade. And this includes any future big telescope. So not long after Hubble launched, analyses were done, people got together, what's next? And what they recommended was an infrared observatory. In 2000, the 2001 Decadal Committee approved this as the next big telescope. And a year later, in 2002, Northrop Grumman won the build competition, and JWST development started. Its cost, and there's been a number of numbers out there, it was around $10 billion. And this is about twice the typical big telescope, the cost of a big telescope. And so a bit more than expected, but it's commensurate with the much greater complexity of this telescope compared to the others. And it is the biggest, most complex telescope ever launched. And if you want to see what it's like, this upper picture is a full-scale scale model of the telescope on the lawn at Goddard Space Flight Center, and some of the people that have been were working on it. Shows you the size. The bottom picture gives you a comparison to Hubble, and these are the two mirrors. And remember, it's the mirror size that makes the power of the telescope. And you can see that the Webb mirror is enormous compared to the Hubble mirror. So what is James Webb? It's a 6.5 meter, and in the picture of the telescope on the right, it's the gold area. That's 6.5 meters in diameter, 21 feet, and it's composed of 18 hexagonal segments. And the whole telescope was passively cooled to 55 degrees above absolute zero, or about minus 360 Fahrenheit. And then that's done passively. The reason it's segmented is that we don't have a rocket that could launch a 6.5 meter diameter object. So it had to be folded up. And so this is a picture of the Ariane launch vehicle and a blow up of the Webb telescope sitting in the nose cone, and it was a tight fit even with this. And so there's only actually centimeters of clearance on the sides of the nose cone. So now getting to the telescope, light comes in from the right, strikes the primary mirror, hits a secondary mirror, which is about a little less than a meter in diameter, and goes down that central dark area. And if you look carefully there, you'll see a little hole, and the light goes through that little hole into the instruments which are behind the telescope. And that little structure there is what ensures that the light that from other areas that we don't want to get into the telescope doesn't get in there. So it's essentially a baffle to make sure that we only see the part of the sky that we want to see. Now below the telescope is the thing that keeps it cold. It's a 5-layer sun shield. It's basically just a giant umbrella. Now if you look at in terms of SPF, this is I think something like SPF of 1 million or 1.5 million, something like that. So it makes it very cold. Space is cold, and so by not seeing the sun, the telescope cools to the low temperature, the minus 360 degrees Fahrenheit. There are 4 instruments on this. Actually, I should mention, below the sun shield is the spacecraft. That's the box that you see there, and the Earth that sees the Earth. So it has all the electronics, it has the communications. Power is supplied through sunlight. The solar array, which you can only partially see, is there. It generates about 2 kilowatts of power. And so that's much more than what the telescope needs. And the one funny thing that's sitting there is that momentum flap. And the reason that's there is because the sunlight produces actually a torque on this. It actually, on the sun shield, acts as a sail. And this is basically a counterbalance for that, so they don't have to keep firing thrusters to keep it stable. This is the spectral region. Like I said, this is an infrared telescope. It overlaps a little bit with the Hubble telescope. Hubble is primarily in the visual. It goes a little bit into the ultraviolet and a little bit into the infrared. And the James Webb Space Telescope picks up a little bit before where Hubble ends, so there is some overlap, and it extends out into the infrared. All right, so 4 instruments. I'm not going to go into much detail here. If you want details on them, you can find them on this website. But the top two, the near infrared camera called NIRCam and the near infrared spectrograph, NIRSpec, have the same wavelength coverage. The camera obviously takes pictures and the spectrograph takes spectra. These two are the primary workhorse for Webb. They do much of the observations, either imaging or spectroscopy. There's a fine guidance sensor and a small science instrument that's supplied by the Canadian Space Agency. Its primary job is to keep Webb stable when it's doing observations. So it's the guidance system for the telescope. And the last instrument is the long wavelength instrument. This was submitted, built by the Europeans with some contribution from NASA JPL. And it's the long wavelength, and this goes out to 28 microns. So these science instruments are not small. As you can see in this image here, each is fairly large. These are human size or bigger instruments. So people tend to think of science instruments as being small. This is not the case for these. They're quite large instruments. So where is Webb? So it's in orbit around the sun. It does not orbit the Earth. It orbits the sun about 1.5 million kilometers, about 1 million miles further out from the sun than the Earth is. And it's slightly inclined to the Earth's orbit. And the reason for that is that the Earth's shadow extends much more than 1.5 million kilometers. And so if we were to put it directly in line with the Earth, it would never see the sun. And so that would be a problem for power. The one thing about this figure that I want to point out is nothing in this graphic is to scale. You want the Earth to scale, it's that green dot in this image. That's the Earth to scale. And the sun, if you wanted it to scale, would actually be about the length of the 1.5 million kilometer arrow. The sun is about 1.4 million kilometers. But it would be located about a football field away to the left. And so space is pretty empty. So the one advantage of this orbit, why it was put in this orbit, is it puts all of the things that would compromise the observations, all the heat sources, all the light sources, all in one area. And so it's very easy then to block those and ensure that the telescope stays cool and dark. So this was chosen for this very specific reason. The one other little quirk with this is if you see a lot of the things that are in the media about Webb's orbit, you see it tracing out a little circle around what appears to be nothing. And this is as seen from the Earth, because its orbit is slightly longer period than the Earth, but periodically they nudge it so that it falls a little bit behind the Earth and then it catches up again. So as seen from the Earth, it looks like it's tracing out this little loop around nothing in space, but it's not orbiting nothing, it's orbiting the sun. I want to get a little bit into some of the technical background about the images. And one of the things that I want to stress is that all the color images you see from James Webb are not true colors. And the primary reason for that is there are no true colors. This is an infrared telescope. It's beyond the scope of human vision. So if you want to simulate the wavelengths that how the Webb is sensitive to, turn your oven on to 400 degrees and open the door and see what color the heat coming out is. And so there is no color for this. And so everything is done with a color palette. And so most of the time they will assign the blue color to the shortest wavelength in the image and the red color to the longest wavelength in the image. But not always. There are times when they want to highlight emissions or something from a particular element or something. So always look at what the color palette is for them, because it is up to the observer or to the person processing the data to choose the color palette. And some of the public release stuff are done just for beauty. They really do look at it as art and choose a color palette that makes it look pretty. One other factor with these images is these spikes that you see all over the place are artifacts. They're the result of diffraction of light off of edges of the telescope structures. And so the individual hexagonal segments, the secondary mirror, the structure to support the secondary mirror, all produce diffraction. And the net result is we get this nice little 8-point star that is in all the images. And even the fainter stuff, you may not be able to clearly see it, but they're there and they do show up in the data. So spectrum, elements have a fixed pattern of energy that they emit and absorb. And the two red arrows in the left image, that left image is spectra of 5 elements, hydrogen through iron, to give you some example. And the arrows point to 2 of the bright features in the hydrogen spectrum. Those are dictated by the structure of the atom, and so those don't change over time. They don't change in any way. But if the gas is moving towards you or moving away from you, you will see a shift in those. And so spectra is where most of the information that we get on objects comes from. It tells us how fast they're moving, what they're made out of. All the physical parameters come from the spectrum. Now, what is the spectrum? In the rightmost image on the left, you see the white ball, and light is coming straight to us. There's no gas in between. And so it produces a continuous spectrum. You can see this if you use a prism for the sun. And actually the shape of that, you can actually use to determine the temperature. But if you put gas, either seeing gas in space against a dark background, or you put gas between the light source and you now start seeing evidence of the elements that are in the gas. And so they show up as these little features, things like on the right, but now mixed together. And so even for a star, stars have atmospheres. And so the light coming from the star will go through the atmosphere, and you will see dark lines in this case because they absorb out the light from the source. And even for the sun, if you get a good enough prism, you can actually see some of the lines in the sun. So it's actually not that hard to do. So questions on this section. What I forgot to mention at the beginning is at the end of each section, I'll open it up for questions because each section is going to be considerably different. And rather than trying to remember what question you had on the first chart, I broke it up into individual sections. So are there questions regarding this introduction?
And Ron, it's a webinar format too, so I'll keep an eye on Zoom.
Okay.
You can ask questions. I think I did see here.
I might have missed this, but is there a navigation control? And if there is, how long does it take to control signal?
Question is there a navigation control for Webb? And yes, there is. There is a group that monitors the position all the time. The torques from the sun are not predictable, and so they every day they monitor. It is basically radar. There's a ranging radar that tells you where it's at and stuff. And there are people that monitor that all the time. And every few weeks they have to do a little tweak on it. But yeah, it's monitored very, very steadily. Basically, this is true for even Earth orbiting satellites. They're always watching where they're at.
Yeah, question regarding the spectrum background you showed earlier, color. The spectrum background is standard one more or less, without a gas in front of it. That represents what our colors would be without something in front of it.
Yeah, correct. So the question was about the spectrum.
Yeah.
So yes, and then the spectrum is the normal colors,
Okay.
and it would be superimposed on that.
Now, the normal colors you speak of, that's because of our sun. If you were looking at a different sun, is it possible you have a different?
No, so this is the same everywhere.
All the stars would have.
All the
that.
stars have the same thing. Now, stars will change the color from being very blue to very red, depending on how hot they are, but basically they're all the same.
Ron, your description of the location of the telescope was a little easier to understand. We normally read. Did you have another way of describing the Lagrange points, or is it just not really true that it's at a Lagrange point in the Earth's orbit? Because
the question was about the orbit, and there's a person from the past who generated this gravitational field, and it turns out with two bodies, the Earth and the Moon, you have these little islands of stability, and these are called Lagrange points. And there are areas there that are the gravitational gradients are low, and those are interesting for something like Webb because we can put a telescope there, and it basically is stable to within some degree. They're not strictly stable, and we would love to have put Webb at one of the Lagrange points because then it's much easier to keep it there. But that's the problem with the Earth's shadow. And so these Lagrange points there's 5 of them, and there's one in front of the Earth, closer to the sun, one behind, a couple on the sides. And they actually do collect dust. There's actually some small rocks that get trapped in some of these Lagrange points because they're basically a saddle point in a gravitational field, and so they're stable. And so a lot of satellites now, both those that study the sun are put towards the one closest to the sun. Astronomers put them towards the back, away from the sun. But yeah, these are part of the structure that was used to choose this orbit.
Is there any concern about a meteor?
Oh, yes. In fact, the limiting fact, the question was, is there any concern about meteors? And absolutely. In fact, the expectation is that the demise of the telescope will be micrometeoroids striking the sun shield and punching enough holes that the telescope can no longer stay cool. And that's part of the reason there are 5 layers. The micrometeoroids will vaporize when they hit the first one, and some of it will splash through the second one. And so 5 layers was deemed enough to get it through at least a 10-year lifetime. Also, micrometeorites will hit the mirror. They generally don't cause that much damage. They do produce little pits, but those aren't really going to affect things a whole lot. Obviously, a bigger one would have a bigger problem.
What was the initial estimate of the cost of building the Webb?
The first real cost was about $4 billion. The $1 billion that's often, the question was about cost. The $1 billion actually was totally spurious. When this first was conceived, the director said, "Oh wow, it'd be really kind of nice if we could build this for just $1 billion," and that's where it came from. And so it's sort of thing of, I want to put an addition on my house. Well, it shouldn't only cost a couple $100. And so nice wishful thinking, but reality eventually dawned.
There were a consortium that took all these different countries.
Oh yes, yeah, and so this is a big expensive telescope, very complex. Any more?
Could you tell us some of the other countries that help?
There are actually other contributions from other European countries that contribute. The European Space Agency is a consortium of all these countries, but they also have been individually contributed either instruments or some aspect of this. There are, I think, a couple of South American countries that have contributed. I don't have the list in front of me. I think there are a couple of Asian countries that contributed. I think Japan contributed, but primarily it was the 3 big agencies: the U.S. Space Agency, European Space Agency, and the Canadian Space Agency.
What size rocket does it take to get something this big up there, or are all those rockets like Artemis and space, or like all the different rockets are shooting up? Are they?
The question was about the rockets, how big of a rocket, and the newer rockets like from SpaceX, their Starship is a bigger fairing and would be able to launch something this size, but not a whole lot bigger. So right now, what people are talking about for the next generation of big telescopes, and I'll get to that at the end of the talk, are things that are 10, 15 meters in diameter. There's nothing that can launch it. So what we're looking at now, and even from folding up things, there's only so much you can fold. And so I'm part of a group that is looking at how you would build these in space. So you would just launch pieces up and then build it in space. Because again, as I mentioned at the beginning, size matters. And so if I can get a 20-meter telescope up, why would I want to deal with a 5? And so we have to basically become more adept in space so that we can actually start building things there. Any more questions? In the back. This is an infrared telescope. Infrared is heat. And so if you have a 500-degree telescope and you're looking at a 400-degree object, you're not going to see anything. And so what you want to do is get it as cold as possible. And without any kind of assistance, you can get somewhere between 40 and 50 degrees above absolute zero. And so that is usually going to be enough, but there are telescope concepts that are being considered where it would be actively cooled to get it even colder, so you could see even more distant objects. All right, I will move on to the next section. So the next section is the early universe. This has had a lot of discussion, and this is one of the primary reasons why Webb was built. The goal here was to tell us how the first stars and galaxies formed, how the first black holes formed. We also, since we know nothing about dark matter or dark energy, what was going on in the early universe with dark matter and dark energy? Were they same, bigger, smaller? So, and there are discrepancies. They're small, less than 10%, between the techniques we use to determine the age of the universe. So the hope is that Webb will eventually clarify this and give us much more solid numbers. The thing is, from the Earth, the early universe, the light from the early universe is shifted into the infrared. This is because the universe is expanding. And so something that is seen in the visual, like we would look at nearby galaxies, is shifted into the infrared at the edge of the universe. So this is why we built an infrared telescope. The goal here was to be able to see this early universe clearly in the infrared. And so, as I said, as something moves away, it is shifted to the red. So blue light becomes red light becomes infrared light. And so the farther back you go, the bigger the shift. Astronomers have developed a simple formula for this, something called redshift, and it's labeled as Z. And you will see in any discussion of the early universe or galaxies, someone will state Z, and Z is the parameter that everybody uses to sort of relate things. It is related to distance, but it's not a simple relationship. So there's not a linear relationship. So if someone says this is so many millions of light years away, there is some dispute over how you obtain that. But if you say it's got a Z of a certain number, that's a simple number. And Z is a very simple thing. It is the wavelength that you observe the light at. So remember those features in the spectrum. It's the wavelength that you see that at divided by the wavelength that you know it was emitted at. So it's a very simple thing, but they also add a -1 to it. And the reason for that is if Z is 0, then it's local. It's not moving significantly relative to us. But the bigger the Z, the further it is away. But like I said, if you want to relate that to a specific number of kilometers or light years, that's a little more complicated. So the image below is a graphic of the universe. And so we're on the right. So this is the universe today. And the Big Bang was at the other end of the figure on the left. The white box is the prime discovery area for James Webb. And stuff to the right is our sort of normal universe, and that's being observed by Hubble and other telescopes, ground-based telescopes included. To the left of the white box, there are no stars. So James Webb can't do anything there because there's nothing for it to see. And so it's that central box that is their prime discovery area. And this is when the first stars turn on, when you start seeing the first galaxies form, first black holes form. And so this is the primary reason this telescope was built, is to understand this phase of the universe. I should also point out that the time scale at the bottom is not linear. So it goes from 0 to 13 billion years by the time you get to the box, and then there's only another few hundred million years to the left. So the universe formed things fairly quickly, and they're very certain that this figure will change once more data comes in from Webb, because everything seems to be moving to the left. So I want to give you an example of how they determine this, and also at the same time provide a little bit of insight into how much of this you should believe at this point in time. So as John Mather said, we're just seeing a lot of stuff far earlier than we thought. They look more mature, bigger. Everything was just not what we expected. So the one thing this makes clear is that we obviously didn't know didn't know as much as we thought we did. So that was not a surprise. But the interpretation of this is still ongoing. Remember, this telescope's only been operating for a year, and they're still learning a bit of things. So this figure is one that was taken to show how they identified things much further away than before. And what I've done here is underlined the Z parameters. And the top one is 13, bottom one is 10. They're down in Z as you go there. And what you're looking at in the data is brightness versus wavelength. And so and the shape down there is what they're looking for here. And so the discontinuity there is the Lyman break, and that's caused by hydrogen. And hydrogen is very efficient at absorbing light. And this is at the rest wavelength of around 90 nanometers. So this is very much in the ultraviolet. Here at the early universe, it's shifted into the infrared. And so what the authors of this paper are saying is that first frame at the top, they've drawn a red line where they think they see that edge. And I don't know about you, but I don't quite see the edge there. You know, obviously the author can interpret it. The next frame down, that's a little bit better. Maybe I'll believe that. I'm not quite sure yet. The third frame down, yeah, that kind of looks like what I'm looking for. So I tend to believe that. And the fourth one, yeah, maybe. And so the point of this chart is really be skeptical. This is really early data. They're trying to figure out what's going on. And so don't assume that everything is correct here. These will change over time as more data comes in. But, you know, the bottom line is that without qualification, there are too many galaxies too early in the universe. So we know something is wrong with our predictions. And so what are some of the possible explanations that people are talking about? Certainly, every telescope undergoes recalibration once they're in orbit. Things, when you arrive in space, aren't quite like what you expected on the ground. And so there's always going to be some recalibrations. So far, there's been no surprises for Webb, so this is probably a very small effect and won't really affect the results. Some of the assumptions that are being made are not going to prove out. That we already know to be true. For example, some of those objects that were shown in the previous chart have gotten better data, and the Z parameter has reduced. So the galaxies are not as old as we thought. So there will be certainly impacts of that. The influence of dark energy and dark matter. We know that they will have probably a very strong impact on the early universe. And since we know nothing about them, it's not surprising that our predictions weren't very good. One interesting thing here, there was a paper published last month that presents a completely new explanation of dark energy. And it would fundamentally alter our understanding of how what it is and how it helped create the universe. Their analysis is very impressive and very compelling. It's only been out in print for a month, and people are already, and it does make predictions, and so people are trying to validate this. But if this were to be proven, then it would certainly alter how we think the early universe evolved. Similar, we don't know how stars formed in the early universe. It's a very different environment than we see today. And so it's possible that stars formed in very different ways. The problem here is we had no data. So while there are many suggestions, without data, we really can't make any predictions. And that is obviously changing with Webb. And again, here, there's a paper that is under review now that I've heard some rumors about. And it suggests that given more reasonable models of what the early universe was like, that stars maybe 100 times bigger than the biggest stars we see today would be forming. And these would form very fast, would live very short times, and could explain much, possibly even all of the issues that we find with the early universe. So bottom line here, like the last time, is be skeptical about the statements. Wait about 6 to 12 months, and I think we'll have a much clearer view of what's going on. One last thing on the early universe. One of the most powerful tools that we have to study the early universe is a gravitational lens. And this is an outcome of the general theory of relativity, and was first proven in 1919. So this has been around for over 100 years. Any large mass, the sun, stars, black holes, galaxies, warp space around it. Technically, you and I warp space around us. It's not enough to really matter. And the bigger the mass, the bigger the distortion. light travels in straight lines, and light is not affected by gravity. But when light is traveling near a big mass and encounters the warp space, it will change direction because it's traveling in space. It doesn't see gravity, it sees space, and space is bent, so it's going to bend. Very large masses produce very, very large bending, and these become basically gravitational lenses. They're the equivalent of an optical lens because they are distorted enough to bend the light enough to focus it in other areas. And the other aspect, like a lens, it magnifies it. So unfortunately, it also distorts it because there's not a smooth field here. This is a lumpy mirror or a lumpy lens. And so it is like looking through old glass. You get all kinds of distortions in the image. But with some effort, you can remove those. And so this allows us to see very distant objects that would be normally invisible to us because they are focused towards us and bent so that the Earth can see it. As this image here shows, the distant source and the Earth at the other end and the cluster of galaxies in between. That's our lens, which is a very poor lens. And so this then allows us to see galaxies that otherwise would be invisible to us. And as an example of this, this is the first deep image that Webb produced, and all those curved galaxies you see are all distorted galaxies that are much more distant than the cluster of galaxies in front of us, and they're distorted and made much magnified for us to see. So that's it for this section. So questions on the early universe?
There was a question that came in on Zoom, but for the last section, there was a person who's curious about the cost of the telescope. And was the cost shared amongst the participating nations?
Yes.
Can you repeat the question?
Oh, well, there was a question from the last section. Was the cost of Webb shared with all the nations? Yes. Everybody pitched in their own money to do this. The Europeans built their own instruments. They supplied the launcher free of charge to NASA. So yes, everybody shared in the cost. Questions?
So redshift always messes me up. So I know you look at the light as it arrives, but where it's coming from, how do you determine what the wavelength might have been from where?
The question was about redshift. Is that he understands that it's redshifted, but how do we determine the original wavelength? That gets back to the atoms. And so what you look for is a signature of a hydrogen atom, and you will then determine, this feature is this transition in the hydrogen atom, and so you know the emitted wavelength. So basically, you first have to identify what is it that you're looking at, and sometimes that's not easy. But once you do that, then you have an estimate because you know that the atom is the same in the early universe as it is today, and so it's going to generate. It's going to produce a feature of the same position.
Something like an object was far enough away in space from us that was like moving away from us fast enough. Could it be like redshifted enough to be like practically invisible without technically actually?
No. Question was about could the object itself be moving fast enough? And we typically don't see that high velocities. There are velocities associated with all these objects. And so if you look at a cluster of galaxies, each individual galaxy has its own velocity, but they are small compared to the velocity imposed by the expanding universe. In principle, yes, you could have something that is ejected at very high velocities. We do see gas clouds that are ejected from objects that are traveling close to the speed of light. So there are features like that. The other aspect that people don't really think about is if you look at something like the Andromeda Galaxy, the appearance that we see, the most distant edges of the Andromeda Galaxy were emitted at a different time than the nearer edges. And so we actually don't really see it what it looks like. The distance is sufficiently small and things don't change that much that it's still a useful thing. But yes, I mean, in principle, there could be objects that are moving at a high enough velocity to alter the ratio. Any more questions? All right, moving on. Now I'm going to talk about clusters of galaxies and clusters of galaxies. And this is a cluster, goes, and you'll find this in astronomy a lot. Abell catalog, it's a catalog, it's just a number in the catalog. So this is the 2,744th entry in this catalog. And you'll see a lot of that. It's been nicknamed the Pandora cluster, and I'll explain what this is. But galaxies congregate into groups, and these can range from very small groups, like our local group, which has a small number of galaxies. A couple of big galaxies and a handful of small ones, to enormous clusters of more than 500,000 galaxies. Abell 2744 is a fairly large galaxy cluster, and it appears to be a merger of at least 4, maybe 5 smaller clusters. And it was named the Pandora cluster by the first person to study it in detail, because they saw a huge range of strange phenomena that are unleashed by the collision. So we said this is like looking into Pandora's box, and the name stuck. And so this is now being called the Pandora cluster. Some interesting tidbits. We can, from the data we have right now, it looks like the merger started about 350 million years ago when the galaxies started colliding. There's about 2,000 galaxies, maybe a bit more, in this image. And if you count up the galaxies, they amount to about 5% of the mass of the cluster. When galaxy clusters collide, there's a lot of gas associated with them, and those gas clouds run into each other, and they do so at high velocity, and so they actually generate a lot of X-rays. And so if you were to look at this galaxy, or this cluster of galaxies in the X-rays, what you'd see is a huge cloud of radiation everywhere. And that's the cluster gas radiating in the X-rays. If you count that up, you've got roughly 20% of the mass of the cluster. So that's 25%. That means that 75% of the mass of this cluster is in invisible dark matter. So this is going to become a gold mine for trying to understand what is dark matter, how does it affect things, is it uniform in here, is it lumpy? And from a variety of things that they can do, they will be able to do this. So you'll be seeing a lot of future information coming on this, as this cluster is telling us this is one of the characteristics of dark matter. So look forward to a lot of interesting data from this. One of the other big things that Webb will be doing is it can see deeply into galaxies thanks to the infrared wavelengths. And its resolution allows us to better characterize what's going on in some of these centers of galaxies and very distant that distances from us beyond what Hubble can see. And so what they use for this is a new type of instrument. It was initially developed for Earth science and is now being adopted by pretty much everybody. It's called an integral field unit. And what it does, and this is a data cube, as it's called, and it simultaneously takes images and spectra. And so what you have is a two-dimensional image, and then a third dimension, you have wavelength. And so this allows you to map out things both in terms of space and speed. And so what they've done here with this data cube is this is a extremely red quasar, and they were looking at the center of the quasar, looking at velocity at motions. And so if you look at the bottom left, the blue image, it shows gas that is moving towards us at 350 kilometers per second. So this is gas that's coming at us. The green is gas that is stationary relative to us. Remember, this is all relative to us. And so it's not moving. The stuff in the orange image, the next image, is at 370 kilometers per second away from us. So this is moving away. And the last frame in the red is even higher at 700 kilometers per second away from us. So almost twice the speed of the other one. Now, what do these mean? Well, if you look at the blue image and the orange image, you might think that's showing some kind of rotation around that central object. I'll have to wait for more data. The high velocity thing on the right is some sort of jet or artifact of something coming probably out of the galaxy. And this is, again, something that is work in progress, but you'll see a lot more of this, and we'll start understanding what's going on in the black holes at the centers of some of these galaxies. One question I always get asked was, what do we look like? Well, this is what the Milky Way would look like from afar. So in searching the images of the people were taking of various galaxies, various fields, someone noticed this one galaxy, and again, it has a catalog name, Leda 204-6648, looked like a spitting image of what we think our galaxy looks like. And so on the right is a science-based rendition of what we would think our galaxy would look like from a distance. And so you can see they're actually reasonably similar. So that would be someone in this galaxy looking back at us would probably see this. One question that if I show a picture of our galaxy is, where are we? Well, we're actually at the center of that little white box there. And if you look very carefully, and I doubt if you can see it, there's a little blue dot there. And that's where the blue dot is. And that's where it is in this expansion. That's a 200 to 300, I don't remember which it is, a light year diameter area. And that is the extent of our human broadcast. So if we were telling people we are here, that's the part of the galaxy that will say, I hear you. And so as you can see, we're pretty much unknown in the galaxy. So any questions on galaxies?
In that last one you showed, how is the galaxy oriented to where Webb is pointed?
You mean in terms of, the question was, how's the galaxy oriented? In this figure,
so if we were in that box, is Webb pointed towards?
Oh, no, the picture on the right is not from Webb. Webb couldn't see anything. You can't see our own galaxy very well.
Well, I'm just saying.
Oh, this would be,
if that were us,
right.
Which way is Webb looking? Just interested in.
Oh, it sees the whole sky, so it can look, look in all directions. At some point, it will also look at the galactic center. So it can sample the whole sky. It can't see all the sky at once, but over a year's time, it will be able to look at anything, any spot in the sky.
Okay.
The first series of galaxies that you said was 350 million light years away, or 350 million years old.
Yeah.
How is that determination made?
By looking at, in this case, it's coming mostly from the gas, the X-ray gas, how hot it is. We know the physical conditions in it, so they can say, well, if it had happened a billion years ago, it would be much cooler than this. It would have had time to cool off. But looking at the density, the temperature, we can determine roughly when things started.
Can you repeat what he asked?
Oh, the question was, how do we know that this occurred 350 million years ago? And the reason is that we use, in this case, the hot gas from the X-rays to estimate how long it would take, how long it takes to heat it up, how long it takes to cool off. And it's a rough estimate. It's not going to be accurate for more than probably 100 million years, but it gives you some idea that this is basically recent, not ancient. And remember, astronomers deal with very different time scales, and very different distance scales.
You know, there's speculations on what dark matter is.
There are lots of speculations. The question is, what is dark matter? There are lots of speculations on what is dark matter. Again, there has been no detection of dark matter except the fact that it's gravitational. So we know that it has gravity associated with it. And there are anything from subatomic particles that are very non-interactive to micro black holes to all kinds of exotic objects that are suggested of a possible source. We're still trying to figure out, you know, somebody please find a piece of dark matter in the laboratory or something. So it's all speculation. With the data that's coming in from Webb, there's likely to be more constraints put on dark matter. It's like in terms of a Pandora cluster. If we really do have 4 or 5 groups colliding, the dark matter has got to interact somehow. And so maybe by looking at how it's distorting things or how things are distorted, we'll get some further insight.
So because you say it's got gravity associated with it, that means it's got mass.
Okay, the question was, if it has gravity associated with it, it must have mass. Yes, that is the general conclusion. Is that, this is mass of some kind. Everything we have seen says that dark matter behaves like a mass, except it doesn't interact with anything. And so in principle, it could be passing through us right now. We just don't know what it is. And this is one of the big mysteries. Since it comprises 5 times as much material as you see around you, probably important that we figure out what it is. And so, it's one of these things where this was a big surprise. It's actually been known for a while. When I was a graduate student, there were big debates about what was called basically missing mass. So it's been known since the 1920s. And it was just never firmly established until fairly relatively recently that it really is a big issue. And it is a form of something that has mass, but otherwise it doesn't seem to have any other properties. So very bizarre.
I have a couple questions from our Zoom audience. First one, what galaxies are in our cluster?
Hey, the question is what galaxies are in our cluster? The Andromeda Galaxy and us are the 2 big ones, and we're actually on the verge of colliding. Come back in a couple, billion years or so, and we'll actually collide, and eventually we'll actually merge into one galaxy. Andromeda is much bigger than we are, and so it'll eat us up. There's another smaller galaxy called the Triangulum Galaxy, which is much smaller than the Milky Way and Andromeda. And then there's the Magellanic Clouds, and then there's a whole host of very tiny galaxies that go by various catalog names. But we're pretty tiny.
Okay, the next one is some of the distant light that the telescope is seeing 1 billion light years old? Is that an appropriate context in which to be thinking?
Yes. And so what we're seeing the question is, what about if the light from a galaxy is 1 billion years old, is that an appropriate way to think? And the answer is yes, is that light travels at a fixed speed, and so it takes time to get here. And so if we see these galaxies that are 1 billion light years away, what we're seeing the galaxy is as it was 1 billion years ago. We're not seeing it as it is today. We start getting into much more esoteric things about what is today, because light is how we communicate. And so, yes, if I can instantaneously transport 1 million light years away and see something, it would look different. But kind of defeats, you can't do that. And so light is as fast as you can travel.
Then last question from the Zoom audience is a housekeeping issue. How much of an issue are other satellites or other space junk? And are there regulations for launching satellites?
For Webb at L2, the question was for telescopes and any satellite in orbit, are there issues with other satellites? And yes, there are. For the James Webb Space Telescope, where it sits, there's only a couple other objects in that area now. I think all of them are now turned off, and so they've drifted away. Space junk is a problem. For something like Hubble, it's a big issue. And in fact, there was actually a discussion yesterday about how Starlink and some of these other things are really starting to compromise the observations, because the Starlink satellites are about 100 miles further up than Hubble. So Hubble has to look through them all the time, and more images are being damaged by seeing streaks of these satellites in there. So at some point, if Hubble were young, then it would probably start becoming less effective because of all of the satellites that are being put up for internet and other sorts of things. Deep space, not a problem. It's just too hard to get there. But eventually, science from Earth orbit will be shut down because all these other satellites will at least astrophysics ones. Looking down at the Earth, there's even going to be a problem there with that, because again, if there's so many satellites up there, you can't get a clear picture of what you're looking at. You're going to have an issue.
When are they thinking of turning Hubble off, or is it off?
question is, when are they thinking of turning Hubble off? It is not off, it is still operating. They will probably let it die. The instruments are the things that will fail. Right now, the instruments are all working. There have been issues with age. These instruments have lasted a lot longer than people had expected. So eventually all the instruments will fail. And then they'll, there is the ability to drive it to re-entry, where it will re-enter over the Pacific somewhere and burn up. But as of right now, it will be used to the last possible point. It's still producing tremendously good data. Any other questions? So coming closer to home, inside the Milky Way, and this is actually a picture of a globular cluster from Webb. I want to focus on nebulae, and nebulae, not to be a pun, is a nebulous definition. So the key thing is, one of the things that Webb was designed to do is really try to understand how stars and planets form from clouds of gas and dust. And these are generically called nebulae, and it really is a Latin term for cloud. Early astronomers, when they would look through telescopes, would see a fuzzy patch, and they would just call it a cloud. And since Latin was popular at the time, they called it nebulae. But there's a huge range of nebulae. They range from cold clouds of gas and dust that will have stars coalescing out of them, to clouds of hot gas that are the final spewing of a death throw of a star. So if somebody tells you it's a nebula, you don't know a whole lot about it. You got a little more specific than that. I'll be talking mostly about the nebulae that stars form from, because that was one of the primary drivers for Webb, is to look at star formation. But one thing I want to point out here is although these look pretty tangible and tactile, they're actually extremely tenuous. Most, if you brought them to Earth, would qualify as a vacuum far better than any vacuum we have on the Earth. So don't believe the TVs or movies that show a spacecraft moving through a fog-like nebula. If they were in a real nebula, people inside the spacecraft wouldn't even know that there's a nebula there, at least not visually. So this is the Orion region. This is a particular region called the Orion Bar. And what you're looking at here is the Orion Nebula is a stellar nursery. It's about 2 million years old. And so stars have started forming there about 2 million years ago, what that age means. And what you have here is a picture of the Hubble visible light on the left and the JWST infrared on the right. And you can see a striking difference between the appearances, both in terms of resolution, in that the Webb pictures give you much greater clarity, and then also just some of the depth that you can see through some of the regions where in the Hubble image you can't see because of all the dust. And infrared light, dust allows infrared light to penetrate. And so this is, again, one of the reasons why we want to use Webb to do this, is we want to be able to penetrate these gas and dust clouds to see how stars form. And so what you have here on the upper right is ionized gas, and you have that because off to the upper right, outside the frame here, is a large cluster of bright hot stars that are vaporizing all the gas. To the lower left, you have the cold molecular gas, and the light hasn't gotten there yet. And that wall between them, that bar, is the ionization point. So that is moving to the lower left as the light from those stars evaporate the dust and ionize the gas. So what you're seeing in detail here is up in the upper right, some distance away is the trapezium cluster, and that's the one that is sort of prominent if you look at the Orion Nebula. And it's the primary source of all the exciting energy that's coming out and ionizing this gas. And I've indicated the Orion Bar again. But what I want to do is step through some of this stuff. This object here is Theta 2 Orionis A, which is one of the stars in the Orion Nebula. You might wonder why this is not having a problem, or not doing nasty things to all the gas and dust, and that's because it's about 100 light years in front of the bar. So, the Orion Nebula is actually fairly large, and this is at the front end of this as seen from the Earth. And so, you're not seeing it affect the gas and dust because it's just too far away. And so one of the things when you look at this stuff is you have a two-dimensional image, but you don't know the third dimension. And so you gotta go look at each of these stars and see where they lie with respect to the gas. Going to the next one, the red arrow indicates a star that's just breaking out of its cocoon. So this is truly a newborn star. It's probably less than a few 100,000 years old, probably tens of thousands of years old. And it just broke out. It's turned on a while ago. It's been heating up all the gas and dust around it. Eventually it evaporates it like you were seeing on the Orion Nebula, and it then has just popped out, gotten rid of its dust shell, and is now a newly formed star. Over here on the right top is a premature birth. This is a star that, as you can see in its location, is located too close to the trapezium stars. And so those stars have been evaporating its cocoon from the outside. And so this star is having its dust cloud stripped away. So it would have liked to have been a lot bigger, but all this dust is being blown away before it can accrete it. And so it's going to end up being a smaller star. But this shows you the tremendous capabilities of Webb to see deep into these things. We can actually see the disk that the star is forming from. And in that disk are probably planets forming. And so this is going to become a very important object to try and understand how planets and stars do form. And that little circle at the bottom of the image is the size of the orbit of Neptune. So this dust disk is about the size of our solar system. So this could have been us 4.5 billion years ago. Finally, in this last image are filaments, and these are clouds of gas that are being jostled and pushed around by all the stars that are turning on. So they're running into each other. They're starting to get denser in some spots. Some of these will actually condense into stars. Some will just get blown away as stars turn on. So in essence, what I've shown you here is the reverse evolution of a star. It starts with Theta Orionis A, a star that's been around out of a shell for maybe 250,000 years or so, to one just forming, to one that's a bit premature, the ones that are yet to form. So this is how star formation works. And this is one of the primary goals of Webb, will be to understand how these stars form, how planets form, how do our solar system form, how's our solar system compared to other solar systems. So a lot of information is going to come out of these observations. This is a famous picture on the left. This is the Pillars of Creation from Hubble. And so that's the image that was on everybody's walls for a few years, a decade or so ago. And it's a visible light image. The image on the right is the JWST image of the same region. And as you can see with that, we can see a little bit more through this. In particular, you see the much greater starry background, and that's because we can see through all the gas and dust that we couldn't see through in the Hubble image. And you can see that while the basic structure is the same, some of these things look a little bit thinner. So we're seeing the less dense things. And in particular, look at these two circles. Those are two groups of stars, and you don't see those in the Hubble image because they're behind the dust wall. So they haven't popped out yet in the visible, but they are clearly present here in the infrared. Now, Webb has one more instrument on that can see further into the infrared. And this is what the mid-infrared instrument on our Webb will see looking at this. And you can see again the same structure. You'll note here there are very few stars in the background. This is not because they're obscured. This is far enough in the infrared that these stars don't emit a whole lot here, so they're just simply too faint to be seen with mirroring. And so again, the same structures. What you're looking at in this image is a very, very cold gas. So this is gas that has not had stars yet turning on. So this is still to be formed. And again, this is looking at another star formation. But there are some interesting things there. If you look at these two little circles in the near infrared image, you see two faint little stars. If you look at those two stars, so just to the right of the two pillars, you'll see they're much brighter in the mid-infrared image than they are in the near infrared. And these are stars that have turned on, but they're still deep in their cocoons. So they're heating up all the gas and dust around them, but they're a long way from blasting it out. And if we go further in the infrared, they'll be even brighter. But eventually these will pop out as new stars. So any questions on the Milky Way?
I was just gonna mention, I mean, this is wonderful stuff, but to remind everybody that 100 years ago, the Andromeda galaxy was called the Andromeda Nebula,
Yes.
right? Before we knew about galaxies and Hubble's work and others at the time.
Right. What Jim said was that remember that the Andromeda galaxy was called the Andromeda Nebula for a while, because again, the early observers in the 1800s and stuff didn't have telescopes good enough, and all they saw was a fuzzy patch. And in fact, actually, there was a huge debate finally ended at the end of the 1920s about whether something like the Andromeda was a cloud of gas similar to things that we like the Orion Nebula, or a separate, as they called it, island universe. And it was resolved that it was an island universe. So that's when our perception of the universe expanded from being tiny with the Earth at the center to being enormous, far bigger than anything that we would have expected, and us nowhere near the center of anything.
Question from Zoom. How do we know the speed of light isn't influenced by gravity, mass, orbit, etc.?
Question was, how do we know that the speed of light is not influenced by by gravity or anything else? That's been measured in the laboratory. You can actually measure that. And it turns out, even from the standpoint of watching something like Jupiter's moons, you can determine roughly the speed of light through a variety of factors. So this is a laboratory measurement, and the speed of light is known to a large number of figures. And every time it's been measured, it's invariant. And we also know that it's not affected by gravity, because if the Earth orbiting the sun, I get the same velocity of the speed of light no matter where the Earth is in its orbit. So this is all very clearly determined in the laboratory. Any other questions? All right, now to exoplanets and planets. So this is something that when Webb was first conceived was really not considered to be a big factor, but is now becoming a much bigger science area. And Webb will be able to detect exoplanets, planets orbiting other stars, in two ways. The upper part of this figure shows transits or eclipses. So as a star passes in, as a planet passes in front of its star, you see a drop in light, and this is the little dip that you see in the curve there. And that's because the planet is not very bright, the star is bright, so it covers up a little bit of the surface. And this is no different than a solar eclipse that we would see here. This is one of the ways you can do it. And from that, from timing and measuring the depth and such, you can actually determine characteristics about the planet, how big it is, what the density is, a whole bunch of other stuff. So this is a fairly useful tool for us to use. Now, we could also direct image a planet, but the planet then would have to be fairly far away from the star in order to get out of the glare of the star, because planets are about 100 million times less bright, at least the Earth is, than the star. So they're very, very difficult to detect. So the question is, would Webb ever be able to detect a second Earth? And the universe is a strange place, and we really don't know for sure, but all odds are probably not. Earth is really tiny. We're really close to our star as seen from a distance, and so Webb just doesn't have the resolution to separate it. And in fact, this is just a really difficult thing that may be possible with some special instruments that are being built for the next telescope, on the Roman telescope, which I'll get to shortly. Or more likely, it's going to have to wait till a telescope is launched in the 2030s or 40s before we actually detect a new Earth. So this is an example of that kind of eclipse. And so this is a fairly nearby star. It's only 41 light years away. It's a very small, cool red star. And it has at least one planet orbiting it, but that planet orbits every 2 days. So this is very, very close to the star. One fascinating thing about this planet is almost identical in size to the Earth, same mass, same radius. And so this is truly an Earth. Unfortunately, it's a very hot Earth. It's so close that the estimate is that the surface temperature is 600 degrees. And so this is Webb's first detection, first confirmed exoplanet. So this is a first for Webb. And it's shown in the upper curve. And that looks, if you look at it, it's like the thing I was showing on the previous chart, that dip. But one thing that is, to me, really impressive is that's a 0.05% change. So this whole dip is 0.1% change in signal. This is a very precision measurement. And this early in Webb's history, this is quite a surprise. This is very impressive. Usually takes a while for the calibrations to get to the point where you can do something this tiny. So one of the first questions anybody's going to ask is, all right, so this is an Earth-like planet, but does it have an atmosphere? And that's what the bottom figure is. And the white dots are the data. And somebody said, all right, so is there an atmosphere here? Well, if the atmosphere was mostly methane, it would be the green curve. And that doesn't fit the data very well. So that's probably eliminated. The purple curve is if it had a very thin carbon dioxide atmosphere, like Mars. And, you know, maybe, but it's not clear. The yellow is certainly is nothing. So it's just a bare rock, and that's just as good a fit. So the questions.
Hang on. From the audience, we can just barely make out those curves.
Oh.
Can you take the pointer? Zoom can see it. Can you take the pointer and sketch out the different bits through the data? The results of what you're talking about?
Wait, I have a better pointer. Sure. So this is the green curve. Purple curve is here, and the yellow is a straight line across there. So again, the green curve goes up here and down, and the data doesn't really seem to fit that very well. The purple curve runs through here, goes up a little bit here, maybe supporting that here. So those are the curves that people are talking about. And basically, this is not a fairly good fit. So more likely than not, this is just a bare rock. Sadly, it'd be nice to have a second Earth, but this is not the place you want to live. No air to breathe, and you can get roasted pretty quickly. So another planet. This is something that we don't have in our solar system. This is a hot gas giant, and these are objects that exist in a lot of places in the universe. There are objects like Saturn and Jupiter that are large, but these are all very close to their stars. And so this one in particular is a 4-day period object, and it's got the mass of Saturn, but it's almost twice the size, twice the diameter of Jupiter. And the reason for that is it's got a 4-day period around its star, and the star is a little bit cooler than the sun, but fairly similar. And so its temperature is 1600 degrees Fahrenheit. So the atmosphere is very puffed out. And this was observed by Hubble and others, and so we know a little bit about it because it's actually a fairly easy observation for an exoplanet. What JWST did was firmly confirm the earlier detections, and it found two other molecules indicated by the red arrows here, carbon dioxide and sulfur dioxide. None of this is terribly surprising. The goal of this is really to refine our techniques to understand how to use this type of analysis to go after atmospheres of planets, because what we'd like to do is use this on something that's a little bit more Earth-like. And they haven't found one yet, but this is developing the techniques to allow that to happen. And then here's Webb's first direct image of an exoplanet. And this is, again, another catalog source, Hipparchus 65426. It's a star that's much hotter than the sun and much further away. It's 355 light years distant. Its planet is enormous. It's 9 times the mass of Jupiter. And so this is a huge planet, almost a star. And it orbits its parent star at a distance of 3 times the distance of Neptune. So this will be way, way out in our solar system. And it's got a 630-year period. What I wanted to show here is just an instrument that is on Webb that is the first time we've flown one of these things for this purpose. It's called a coronagraph. And what it is in simple terms, it's got essentially a finger in there. And what it does is hold your thumb out in front of a bright source, it blocks the light, and you can see what's next to it. And that's all this is. It's a very sophisticated finger. And so in the images at the bottom, the fine-pointed white star is where parent star should be. Now, this should be coming through like gangbusters and overwhelm everything in the image. But if you put the finger there, if you look at the redmost image where it says planet, the white star, you can see a little dark area around it. And that's the hole that they put this thing in so that the light doesn't escape. And so the object there is the planet. That's not an artifact, that's all the planet. When you get to the two images on the left with near cam, the structure of the camera is such that it produces those little square artifacts. And so those are just artifacts of the processing and will be removed at some point in the future. And so here we have four image of this one planet at 4 different wavelengths. And from that, they're going to be able to determine whether it has an atmosphere, whether it's a rock, all this kind of stuff. So this is again going to be a fairly major science area for Webb, is the ability to do this, some of these distant planets. Much closer to home, Neptune. Webb can observe objects in the solar system. And this is an image of Neptune taken in the infrared with NIRCam. And this is what you're looking at. That big object, big bright object at the top is the moon Triton. Triton is about the same size as our moon. The disk in the middle with the rings around it is Neptune. And 6 of the 14 moons of Neptune are shown there. This is a surprise. Why is Neptune so much darker and Triton so bright? And the reason is that Neptune's atmosphere is mostly methane. And at these wavelengths, methane absorbs the light. And so Neptune is very dark. Triton is an icy body. And so it reflects about 70% of the sunlight that strikes it. So it's much brighter than Neptune at these wavelengths. And again, if you look at Neptune in detail, see those splotches on the surface? Those are high altitude methane ice clouds, similar to Triton. And those reflect light back from the sun before it gets absorbed by the planetary atmosphere. So from these observations, you're going to be able to tell a lot about dynamics on Neptune. And Neptune is the windiest place in the solar system. It is got the highest winds and continuously high winds. And so it's a very turbulent atmosphere. So there's going to be a lot of videos coming out showing motions of things in the Neptune atmosphere. So any questions on planets? Oh, incidentally, this is an image of an asteroid that is between Jupiter and Saturn that actually has a ring. So how the ring got there and why it's still there, we don't know, but it has a ring. Yeah.
And the planet that you have the 4 images across the bottom, and the ones on the right with the NIRCam or the middle far infrared. I'm not sure what.
The question was, well, this one, the images on the left are from the near infrared, so those are the near infrared images, and then the other 2 on the right are from the far infrared.
And so the light from these, in all cases, is being emitted by the planet.
Yes.
So where do you differentiate between a planet and another star and make this a double star?
This is probably going to be debated about this object for a good bit, because generally speaking, around 10 times the mass of Jupiter, hydrogen turns on in the interior of a body. So this is arguably either going to be a planet or a star. So, and at this point, they'll have to look at the light that's coming from here spectroscopically to decide whether or not it's truly coming from the planet, which in the then case it's a star or it's reflected light. Remember, this star here is a much hotter and brighter star than the sun. So even though this is 3 times the distance of Neptune, it's going to get a lot of light from its parent star.
In current science, what's the probability of finding a planet similar to Earth? How far would that be?
The question was, with current science, how likely are we to find another Earth? The numbers that we have right now are that the most common type of planet It's a planet that's about 2 to 3 times the mass of the Earth. Now, these are going to be rocky planets, so they will be like Earth. We have nothing like them in the solar system, so we don't know whether they will have atmospheres or other things that are suitable for life. That's a big question right now, and people are really trying to gather some information on it. We also know that Earth should be relatively common. It's statistical data, but the distribution of planet masses are such that there should be a lot of Earths out there, and they should be orbiting at similar distances from their stars as we are. So Earths shouldn't be that rare. They're not common, but they shouldn't be that hard to find. Problem is, it's going to be probably at least another 10 or 20 years before we have the technology to see them. And this is being refined continuously. Whether or not these bodies will have atmospheres, more likely than not they will. So the probability of if there is another Earth, it will have an atmosphere. Whether there's life on it, that's the big question. We don't know. We do feel that for the Earth, life was brought here through molecules from the nebula that created the Earth and from asteroids and other things that ran into it. So you would think this would happen everywhere. So these are all technically assumptions, but we should find life. In fact, actually, there's a problem right now we should have detected an alien civilization by now. The fact that we haven't, it's a bit of a puzzle. Either life is much harder to form or intelligent life is much harder to form than we thought, or there are some other factors. And right now, the most likely factor, which might not surprise you, is self-extermination seems to be one of the possibilities for advanced civilizations. Either they pollute their environment or they destroy themselves with weapons or whatever, but we don't know how long intelligent civilization lasts. Any other questions?
It doesn't have to do with the planet, but Roman, what is its focus gonna be? Like,
You're one chart ahead.
oh, sorry.
So the question is the Roman telescope, what's its focus? And so I said you one chart ahead. So I will move on then. So this is what lies ahead. And the Nancy Grace Roman telescope is named after the first astrophysics lead for NASA. And she's a real nice person. And everybody's really pleased to see this named after her. She did a lot of work. One of these people that worked in the background and made a lot of things possible and never got the credit that she deserved during her life. And so the decision to name this telescope after her was well received. So it's currently under construction, and it was the #1 selection from the 2010 decadal. And it's scheduled to launch in 27, maybe a little earlier, maybe a little later. It has the same size mirror as Hubble, but the instruments on it have 100 times larger field of view. And the reason the mirror was the same size as Hubble, it was donated by some government agency who no longer needed the mirror. And so you don't turn away a free gift. And so that's why it's that size. And that made it launch a lot earlier. But its primary goal is to really address dark energy and dark matter. It also has a more sophisticated chronograph, so it's going to be our first test of really using this instrument to study planets. And so it's experimental, and so we don't know how well it's going to work, but those are its primary factors. And then, of course, it does general astrophysics. Beyond the Roman telescope, the 2020 decadal just finished releasing their results, and they actually did something very unusual. They didn't pick one telescope. They said, with all of the rising costs of things, and this is becoming unaffordable, they directed NASA to look at 3 options. A large Hubble follow-on, so this is Hubble on steroids, and it should be at least 6 meters in diameter, so bigger than Webb. And it should contain all the things necessary to study exoplanets. Another option is a very large infrared telescope, a follow-on to Webb, that would be at least 8 meters, so 1.5 to 2 times the size of Webb. And then the X-ray community last launched one of the big X-ray telescopes in 1999. This is the Chandra Observatory, and it's getting pretty old. And so they would like a replacement because we do want to have information on X-ray coming from objects. And so NASA was directed to do technical studies of these, but not decide. And it charged the 2030 decadal, so another 7 years, to making the down select to decide which of these three should go forward. And so then the other thing that's changed is now with NASA returning to the moon, with the Artemis program, the possibility of putting a low frequency radio telescope on the far side of the moon is becoming real. And this is important because in that early universe, there are no stars, but there's lots of hydrogen. So this telescope will actually be able to see those first structures before they form stars and address a lot of the questions that will still exist after Webb is long gone. And so turns out I have a little bias in this because I'm leading a study for this. And this is the Far View telescope. This is an artist's conception. And this is done on the far side of the moon. And it's on the far side of the moon because the Earth is extremely noisy and needs radio wavelengths. The radio wavelengths here are a little bit shorter, a little bit longer wavelength than old TV signals. This is basically VHF and lower frequency. And so the Earth naturally and anthropomorphically generates a tremendous amount of noise. And the moon is a really nice blockage of that. And so the far side of the moon is the quietest place you can be in the inner solar system. And so our plan is to build this radio telescope on the moon using lunar dirt. And what you're looking at here, the light colored bars are dipole antennas, not a whole lot different from the antennas that were on your roof when you were a kid. And then the black curves are power and communication lines. And we're going to build 100,000 of these, and we're going to spread them out over an area much larger than the city of Bend. And this will be able to see back right to when the first structures formed in the 80s. And so with that, I thank you.